This is our first lesson for the new unit on derivatives. So just want to remind you again about the opportunities to read more about what's going on here. This lesson is from the OpenStax textbook that's posted onto Google Classroom, as well as taking a look at the Calculus for Dummies content. We just finished up our first unit on calculus material and limits. And so hopefully you realize, oh, I need to put in more work, or I'm putting the right amount of work in to make sure you know what you're doing. Okay, so we're going to start just in this lesson by defining the derivative, going through these problems, and working through all of these objectives. So the first thing I want to go through is somewhat of a review from the very first lesson in the previous unit, which was an introduction to calculus. And calculus, in this case, what we're focused on in this part of this unit is about tangent lines. Okay, and so what I want to kind of talk about in this figure 3.4 is you have a lot going on here, right? You've got your black curve, you've got your, looks like an orange or red line, and then you've got a blue line, and then maybe even a green line. So the first thing I just want to point out is the green line, all right? And the green line is what we're ultimately going to be trying to find in this unit, which is the equation for a line that is tangent to a function at a point. So that's what we're trying to do. What we did in that first lesson, the intro lesson last unit, what we're going to do a little bit at the beginning of this lesson, but not much, is we talk about how we can estimate that slope of that tangent line by finding a secant line. So essentially we plot another point on the curve, as you can see, with x subscript 1 and then f of x subscript 1. And as we slowly drag that point closer and closer to the point A, then your secant line and your tangent line are going to essentially become one. All right, so you can see it goes from that orange one or red one to the blue one, the x sub 2 and f of x sub 2, right? That's getting closer and closer to being just the same line. Now, this other one here, we didn't really talk much about. This is new in this one, but essentially it's the same thing. I don't want you to worry that it's new. It's really the same thing, but it looks a little different because instead of having like x, and when you plug it into the function, they're saying you take your a value, kind of think of like you're going the other way. You take your a value and you add a value to it. All right, so think of like this h subscript 1 is h subscript 2 as being values that are close to 0. So if we take this a, which is on the x-axis, and add, like 0.5, we're not moving very far to the right. So essentially this second theorem, this second equation we're going to use in some of these questions, I always just used to think of it as you're going, instead of like moving towards the A, that H value is kind of moving, think of it as starting away from the A, and then it will move towards it. So it's going to seem like it's different, and I know it looks different, and the work's going to feel different, but it is essentially doing the same thing. So you really can choose whichever one you want, and we'll be going through how to use both of them, okay? But ultimately, if you look at this last part C, we're trying to find that line in green. All right, so let's try to do it first with that initial equation. So we're trying to find the equation of the line that's tangent to the graph of f of x equals x squared. So that's our parent quadratic function at the point x equals 3. So I'm going to first use this equation, right? So I'm going to write the tangent. So the slope, actually I'm going to put it above it. The slope of our tangent line, all right, is equal to f of x first, my bad, then minus f of a over, Douglas, sorry guys, bear with me. Come on, where's Bob? Uh-oh, it's frozen. Forgot to put the limit, that's my bad. There we go, let's try again. The limit as x approaches a of, here we go, f of x minus f of a over x minus a. Okay, so we're going to be using that equation, that first one, to find the equation for the line that's tangent to this graph at x equals 3. So let's first write down f of x. So I have the limit as x approaches 3 of f of x, which is x squared, minus, and if I were to plug 3 into f of x, right? So essentially I'll change colors to show you some sidebar work here. right? So essentially I'm doing f of 3, which equals 3 squared, which is 9. So I'm going to be plugging in 9 where it says f of a all over x minus a, which is 3. Now, it didn't happen in this one, but just to let you know, remember, if your value for a is negative, just think the opposite in that denominator, right? In the denominator, you can see x minus a, so you have to think opposite when you write what's going on. Now, if I were to try to evaluate this limit, like we did in the first, or in the unit 2, our unit on limits, you would notice I have a problem, right? 3 minus 3 is at 0 in the denominator, and actually 3 squared minus 9 is also 0. So I wouldn't be able to find it, but we know we can factor. All right, we can factor that numerator because it is the difference of two squares. So that's going to be x minus 3 times x plus 3. All right, so that crosses out. And now we have the slope of our tangent line is equal to the limit as x approaches 3 of x plus 3, which we can plug in 3. 3 plus 3 is 6. So the slope of this line is 6. Now, we're not done, right? It doesn't say just find the slope. It says to find the equation of the line. So this is where you're going to be using your algebra skills, using point slope form to find the equation for the line. So we have the slope. We need a point. And the point I'm going to use is actually the one that I just found earlier. And if it's going to be on this line, it needs to cross 3. And 3 squared is 9. All right, so now I'm going to use point slope form. So it's going to be y minus 9 equals 6 times x minus 3. Distribute the 6, and then move the 9 over with addition. So the answer for the equation of the line that's tangent to this curve, f of x equals x squared at x equals 3, is 6x minus 9. Now let me show you kind of the graphical view of what we just did. So I'm going to plot x squared. Okay, so here is x squared, right, parabola. Remember, I'm going to be focusing on 3, 9, which is up here, right? Where is it? There it is, just past it. It's almost at it. There it is, 3, 9. And the point, or the line that we found was 6x minus 9. Let me confirm. Yes. So if you look at that point there, 3, 9, that is the line in blue, or at least my line in blue, is the tangent line to this curve x squared at the point x equals 3. So that's the whole process using that first equation. So now what I want to do is I want to use the other equation. And you're going to see that we're going to get the same answer. All right, but we're just going to find the slope. We're not going to do the whole step or everything to find the line because we already found it. But now I'm going to use the slope of my tangent line is the limit as h approaches 0. Remember, we're getting a smaller value that we're adding to that letter a. So f of a plus h minus f of a over h. So I'm going to use that second equation. So here we go. We've got the limit as h approaches 0 of f of 3 plus h minus f of a, which we already know f of a was 9, all over h. Now I'm going to do a little side work here, and then on your notes, you can do it underneath. I'm going to do it to the side, but you can do it underneath on your paper. So I'm going to do 3 plus h squared, right? I have to do f of 3 plus h. So I'm plugging that in for x. And then if you remember how to expand that binomial, do the first term squared, plus you do 3 times h and then double it, so 6h plus h squared. So that's going to replace f of 3 plus h. So that becomes h squared plus 6h plus 9 minus 9 over h. Just make sure you don't forget to bring down that minus 9, right? Okay, so now the 9s are going to cross out. And we have h squared plus 6h over h. But here's the problem. If I try to plug in 0 for h right now, I'm going to get 0 in the top and the bottom. But you should hopefully notice that we can factor an h out of the numerator. And so that's going to cross out. Those h's cross out, and I'm left with the limit as h approaches 0. Remember, this is equal to the slope of my tangent line. The limit as h approaches 0 of h plus 6. If I now plug in 0 for h, 0 plus 6 is 6. And again, we should already have known we were going to get 6. I'm just showing you the different work using that different formula. So you can use either one you want. I'm going to be showing you a lot in this lesson how to use both of them. Okay, let's keep going. Very similar process. Find the equation of the line tangent to the graph, f of x equals 1 over x at x equals 2. So I'm going to use that equation we used for the very first time, which is the slope of the tangent line is equal to the limit as x approaches a of f of x, there we go, minus f of a over x minus a. Okay, so here we go. Let's find it. So the limit x approaches a of 1 over x minus, and if I plug in 2 where it says x, right, because I'm doing f of 2, that's going to be 1 over 2 or 1/2 over x minus 2. Remember to think opposite here. Again, I'm going to do a little side work. You can do it below or to the side, wherever you have room. I need to do 1 over x. So I'll do it underneath this time. No, I'm going to do it over here. 1 over x minus 1/2. So I need to get a common denominator. That common denominator is 2x. So this is going to be 2 over 2x minus x over 2x. All right, so now I have 2 minus x over 2x. Let's see if you're still following along here with my complex fractions. All right, so we have 2 minus x over 2x divided by x minus 2. So I'm going to rewrite that to be 2 minus x over 2x times 1 over x minus 2. All right, we're still, should have changed that to a to be a 2. Sorry about that. There we go. Now we're still not there yet, because what you'll notice is that we aren't able to cross anything out, right? I'm about to write all this stuff together, but you can't cross anything out. But watch what I do. You'll notice the numerator and the denominator look like they almost have something you can cross out. The numerator has negative x plus 2. Denominator has positive x minus 2. So if I factor out a negative in the numerator to make that a positive x, to make that positive 2 a negative 2, then when I write the denominators together, you'll see I can cross out that common factor. So now I just have negative 1 over 2x. So the slope of my tangent line is the limit as x approaches 2 of negative 1 over 2x. Plug in now. Now I can. And you get negative 1/4. Okay? Now to find the equation, I'm going to use point slope form. We already know that when you plug in 2, you get 1/2. So the point I'm going to use, change colors for you. The point I'm going to use is 2 comma 1/2. And now we're ready to use point slope form. So y minus 1/2 equals the slope of negative 1/4 times x minus 2. So y minus 1/2 equals negative 1/4. And anytime you guys want to switch to decimals instead of the fractions, that's fine by me. So this is going to be positive 2/4, which is 1/2. And so if I move over the negative 1/2 by adding a half, half plus a half is equal to 1. So there is my slope of my tangent line. I'm going to go ahead and plot it. You don't have to do this. I'm just trying to show. I know some people out there appreciate the visuals. I like kind of confirming in my brain when I see it that it makes sense. So I'm graphing 1 over x, and then I'm plotting the points or the line negative 1/4 x plus 1. Scroll a little bit. Here's x equals 2. That point 2 and 1/2. You can see that that purple line is the line that is tangent to this curve at x equals 2. All right, so hopefully you see kind of the algebra with the graphical display here. Okay, now the next part is to kind of put a name to the process that we just did. Okay, so this is something that occurs so often in different fields, like the mention of physics, looking at some business functions, and in science, that they decided to mathematicians hundreds of years ago gave this a name. All right, so this limit that we've been finding is called the derivative. Okay, and the process that you're doing to find it is called differentiation. So these formulas, you'll notice, are exactly the same from the previous couple slides ago, but now they're putting in some notation. And that, how you read that is f prime of a. So this right here, this notation is f prime of a. All right, so that little symbol there means to find the derivative. Okay, so again, the formulas haven't changed. It's just now we're adding that extra piece. Okay, so let's do it first with a table. All right, so we're going to find the derivative of this function f of x at 3, so f prime of 3. All right, so we're going to be plugging in our x values that are just below and just after 3. So it's going to start with 2.9, 2.99, 2.999, and then just past 3, too many zeros there. So something like that. So you'll notice we're like just below 3 and just above 3. And then in terms of what we're going to plug in, this is where we have to use that formula, right? f prime of 3 is the limit as x approaches 3 of f of x minus f of 3 over x minus 3. Okay? So I'm going to plug in this up here, which we just used before, as x squared minus 9 over x minus 3. Now, if you wanted to, you could factor, right? They do have common factors, but I just want to keep it and show you that you don't need to, right? We're not plugging in the value that's going to be an issue. So I'm just going to leave it as x squared minus 9 over x minus 3. All right, so let's plug that in. We can make a table. Oh, no, I don't want to do that. Sorry. Let me do x squared and then make a table. Here we go. Move this out of the way. My first one was 2.9, 2.99, 2.99, 3.001, 3.01, and then 3.1. Okay? So I can write these down as 8.41. So 8.41, 8.9401. Okay, what I realized was as I was doing this, I was not typing in the y value, the equation that I wanted to use, which is x squared minus 9 over x minus 3. So that's my bad. I'm sure you were shouting at the screen here, so I apologize. So x squared minus 9 over x minus 3. Let's try this again. Okay, now I want to duplicate this one, make it a table. Here we go. Now we're cooking. Sorry about that. Okay. Here's what I'll be writing down. Okay, this makes more sense. I was just thinking, I was like, I know the answer is 6. What am I doing wrong? All right, so let me write these numbers down. So 5.9, 5.99, 5.999, 6.001, 6.01, and 6.1. So you can see that as we're approaching it just below 3 and just above 3, as we're approaching from both sides of 3, we're hitting 6. So we are approaching, should say, the the f prime of 3 is 6. Okay? Now, we're going to do the same thing, but we're not going to use a table. We're going to use our algebra to do it. So the same formula applies that I just did, which was f prime of a equals the limit as x approaches a of f of x minus f of a over x minus a. Okay, so I'm going to do f prime of 2 is the limit as x approaches 2 of 3x squared minus 4x plus 1. And then if you plug in 2 to this function, do it to the side here. Oops, sorry. So we're going to do f of 2, which is 3 times 2 squared minus 4 times 2 plus 1, which is, let's see, 2 squared is 4, 3 is 12, minus 8 plus 1. So that's going to be 5. So that's going to be minus 5 all over x minus 2. Okay? So I'm going to simplify the numerator. That's going to be 3x squared minus 4x, and then plus 1 minus 5 is minus 4. Now, you'll notice that if I try to plug in that 2, right, if I try to evaluate this limit by plugging it in, which I'm always hopeful to do, is not actually possible, right? It makes a 0 in the bottom. So I'm going to factor the top, do factors of a times c that add to b. So that's going to be 3 times negative 4, which is negative 12, that add to negative 4. So I'm looking for factors of negative 12 that add to negative 4. So negative 6 and positive 2 should work. So let me do some more work here. So I'm going to rewrite 3x squared minus 6x plus 2x minus 4, factor by grouping. So 3x times x minus 2 plus 2 times x minus 2, and now I have my factors. 3x plus 2 and x minus 2. All right, so replace that in the numerator. Sorry, so the limit as x approaches 2 of 3x plus 2 times x minus 2 over x minus 2. So now I can cross out the common factor and write down that my derivative, all right, of this function at x equals 2 is the limit as x approaches 2 of 3x plus 2, which I can plug in that 2 now. 3 times 2 is 6, and then plus 2 is 8. All right, so that is f prime of 2. It's equal to 8. All right? All right, let's keep going. Now, we're going to do the same thing. All right, now you're like, oh, we just did this, Mr. Frederick. We did, so we know it's going to be 8. All right, but I want to try to use that other one, which says f prime of our a. All right, go back to the slide, show you where I'm getting this from. All right, the second one, f prime of a is the limit as h approaches 0 of f of a plus h minus f of a over, all right, just h. Okay? So that, again, we're using this second one. Okay, so let's do it. Here we go. We're going to do the limit as x approaches, as h approaches 0 of, and I'm going to do some side work here. I guess I'll do a little bit above. I need to figure out what f of a plus h is. I'll do some work over here. So that's going to be 3 times a plus h squared minus 4 times a plus h plus 1. All right, so I'm going to keep going this way. And that's going to be 3 times expanding binomial, so a squared plus 2ah plus h squared minus 4a minus 4h plus 1. Distribute. You get 3a squared plus 6ah plus 3h squared minus 4a minus 4h plus 1. All right, let's combine like terms and put it into our actual problem. So I know I'm going to have 3a squared plus 3h squared plus 6ah. All right, and then I'm going to have minus 4a minus 4h plus 1. And then I have to subtract when I plug in 2 here, which we did before, right? We did before when we plugged in 2, we got 5. That was in that blue, so minus 5. All over h. Okay? Okay, so just a quick kind of catch up where we are. I realized I needed to plug in 2 for a after doing all this. So I don't want to do that later because I want you to know that you should be doing it from the beginning. So let me go back. So I apologize if you wrote all this. But I want to plug in 2 plus h. All right, so erase all that numerator. So I was wondering, I was like, I need to be able to cancel something out. And that's not happening yet. So let's try again. There we go. A is 2. So I'm plugging in 2 for a. So now I have 3 times 2 plus h squared. This makes more sense. Minus 4 times 2 plus h plus 1. All right. Do the same thing, expand a binomial. You get 4 plus 4h plus h squared minus 8 minus 4h plus 1. Distribute 12 plus 12h plus 3h squared minus 8 minus 4h plus 1. Okay, now I'm going to get all some like terms here. So I'm going to write down 3h squared. All right, 12h minus 4h is 8h. Okay, then I have 12 minus 8, which is 4. 4 plus 1 is 5. Don't forget to write your minus number that we got when we plugged it in, which was 5, right? F of 2 is 5 because we did that before, all over h. So the 5s are going to become 0. So the limit as h approaches 0 of 3h squared plus 8h over h. Okay. And now I have, you can notice that I need to factor out an h in the numerator. So h times 3h plus 8 over h. So the h is going to cross out. So we have f prime of 2 is the same as the limit as h approaches 0 of 3h plus 8. So if I plug in 0 for h, I get 3 times 0 plus 8, which is just 8. Whoa. All right. That was amazing. All right. So again, I knew I was going to get 8, but just using that different formula. Okay, let's go to the last part. Now, the last part of this lesson is essentially kind of tying in stuff that we did in that intro lesson from the limits unit about talking about average velocities that we calculated. Oh, excuse me. But essentially, what we're doing here is we're going a step farther than we did in that intro, right? In the intro lesson in last unit, we talked about the average velocity being this change in the distance over the change in time. But now, so what we did last unit when we did that first lesson was we calculated a bunch of average velocities to then estimate the instantaneous velocity of that object at that time t. But now we can actually do that. That's one of the applications of differentiation is we can actually find that instantaneous velocity. So we're going to be using v of a is the instantaneous velocity, which is the same as the differentiation or the derivative of our position function, s of t. So s prime of a, it says to find the derivative of that position function. So we'll be doing the same, very similar work that we've just done, but now I'm going to show you the application for this. Okay, so let's do one with a table. All right, so this one says we have this lead weight suspended from a spring is in vertical oscillatory motion, so it's going up and down, and we want to find the instantaneous velocity at time 0. Okay, so we're going to estimate it first. So we have values for t. All right, and then in terms of what goes there, that's what we're going to find. So v of 0 is the limit as t approaches 0 of, and this is where we're going to have s of t minus s of 0 over t minus 0. Okay, so I'm going to be plugging in, and that's going to be s of t, which is the sine of t, minus the sine of 0 over t, right? T minus 0 is t. And the sine of 0 is actually also 0. So this is going to be the sine of t over t. So that's equal to the instantaneous velocity at time 0. So I'm going to go from values that are just below 0 to just above 0. So just below 0 to just above 0. Okay, and then in for my y values, I'm going to be plugging into sine of t over t. All right, and now when I use Desmos, I'm going to use x, but just so you know, it's very similar to what we did a few examples ago with Desmos and that table. So let's go ahead and clear this one out. We have the sine of x over x. I want to duplicate it, make a table. We're going values that are getting closer to 0 and then just above 0. Okay, and I'll write these down, but you should notice that as we're approaching it from the left and from the right, we're getting closer to 1. So I know that this instantaneous velocity of this oscillating spring when time is 0 is 1, what's the unit? It doesn't give me a unit. 1 unit per time. All right, so I guess probably per second. All right, so let's write them down. 0.99833, 0.99833,417, and 0.49s, and then 8, and then a bunch of 3s. How many 3s? 3 3s? Yep. And then way more 9s. And then an 8 3. And then I think it's the same, but going the other way. Something like that. And then finally, we can see that this instantaneous velocity is equal to 1. Okay? Okay, so now let's do one more, but this time we're going to use our algebra to figure it out using this formula up here, right? Again, it's the same formula that we've been using since that intro lesson in the last unit, but now we've put some names to it with the instantaneous velocity, the v of a, and that's equal to the derivative of your position function at that time a. Okay, so we have a homeowner sets the thermostat to the temperature in the house so that it begins to drop from 70 degrees at 9 p.m. and reaches a low of 60 during the night. Whoa, this is expensive. And rises back to 70 by 7 a.m. the next morning. Suppose the temperature in the house is given by the function temperature at time t of 0.4 t squared minus 4t plus 70 for values for your time between 0 and 10, where 10 is the number of hours past 9 p.m. Okay, so like 1 for t would be 10 p.m. So find the instantaneous rate of change of the temperature at midnight. So midnight, if we're looking at t is the number of hours past 9 p.m., midnight would be t equals 3. So I'm trying to find the instantaneous rate of change of the temperature at midnight. So the instantaneous rate of change would be my, v of 3
which is equal to my t prime of 3, which is the limit as t approaches 3 of t of t minus, move this here, t of 3 over t minus 3. So lots of t's. Hopefully you know that the uppercase t is for temperature and the lowercase t is for time. All right, so let's plug in some stuff here. The limit as t approaches 3. This one's just going to be 0.4 t squared minus 4t plus 70. And I have to subtract what the temperature is when I plug in 3 hours past midnight. So I'm doing t of 3, which is 0.4 times 3 squared minus 4 times 3 plus 70. All right, so let's go to Desmos. We can plug this in. All right, so we have 0.4 times 3 squared minus 4 times 3, and then plus 70, right? Oops, sorry. Plus 70, which is 61.6. All right? So I'm subtracting, change my color back, subtracting 61.6 all over t minus 3. Now, this is the fun part, or at least, I find it fun. Now, when you simplify in the numerator, you have minus 4t, and then this is going to be plus, all right, so that's going to be 8.4, I believe. Yes, 8.4. And you might be thinking, oh, man, well, this is all great, right? We're doing everything fine. But if I want to evaluate this, I got to plug in 3 for t, and that's going to be a problem in the denominator. But wait for it. Oh, this is where it gets super fun. If you factor out, okay, if you factor out 0.4, okay, you actually get t squared, all right, and then this is going to be minus 10t, right? 10 times 0.4 is going to be 4, okay, and then plus, and then this one is, I think it's 21. Let me confirm. I'll show you the 4 as well. So if I do factor out the 0.4, 4 divided by 0.4 is at 10. And then this one is 8.4 divided by 0.4. You get 21. There you go. So you actually are able to factor, once you do that, you get plus 21. And now this is one of those more ones that you factor when you were in probably 9th grade. So you have 0.4 times t, so you need factors of 21 that add to negative 10, t minus 7, and t minus 3. And you'll see that now we can cross out what's in the bottom. So we have the limit as t approaches 3, and this is equal to t prime of 3, which is equal to the instantaneous rate of change at 3 hours past 9 p.m., so at midnight, is equal to 0.4 times t minus 7. So if I plug in my 3, I get 3 minus 7, and this is equal to negative 4 times 0.4, which you probably know the answer, but I'll plug it in just all the same in case you need to see it. So it's 0.4 times 3 minus 7 is negative 1.6 degrees Fahrenheit per hour. So negative 1.4 degrees Fahrenheit per hour. I think that's the right unit. Yes. All right, so the instantaneous rate of change of the temperature exactly at midnight is negative 1.4 degrees Fahrenheit per hour. Wow, that was amazing for an application of derivatives. All right, so hopefully you had a chance to go through this. We've gone over it in class. You're feeling okay on doing the homework. And I apologize for the mistakes that I made, but just showing you that I'm learning how to do this just like you.